So last time we covered, well, we started working on partial fraction decomposition. We did a couple of examples. We have a look at where these partial fractions are coming from, which is essentially the backwards problem of that problem in intermediate algebra in which we were asked to combine fractions together. So this time we have a big fraction. We need to split it into a sum or difference, depending on the signs of the coefficients, of simpler fractions or partial fractions. Now, for example number 4, things are going to work a little differently than what we did in the previous example. So let me get my stuff ready. And okay, it's right here. So number 1, for the next example, notice how we have this x plus 1 factor. And by the way, this factor x plus 1 is a linear factor. Don't be fooled by the power on the exponent here. You might think, well, that's kind of a quadratic factor. I think it looks like quadratic, but it's not a quadratic. So what we're going to do in this case is, not for x, a over x plus 1 plus b over x plus 1 quantity squared. That's what the guidelines tell us to do for repeated factors. For example, let me make something up real quick on the side. If we had something like the integral of x plus 3 to the 4th power times x minus 7 to the 3rd power dx, well, then we would have to write every single power of x plus 3 up to the 4th power. That is the integral of a over x plus 3 plus b over x plus 3 quantity squared plus c over x plus 3 to the 3rd power plus d over x plus 3 to the 4th power, and then in this case we got to the highest power of x plus 3. Let's write the next one. X minus 7 a b c d e plus f over x minus 7 squared and g over x minus 7 cubed dx. Alright? Are we going to do anything like this? No. We're not going to do anything this crazy. But this side trip right here is just so you can see how we would expand it whenever we have repeated factors. Alright, so let's go back to our example that we have here. Well, so number 1, we need to figure out those those unknowns a and b, and to do that we're going to set the expression on this integrand equal to the expression on the integral in the previous step. That is 4x plus 7 over x plus 1 squared equals to a over x plus 1 plus b over x plus 1 squared. So you don't want to work with an equation this complicated. So number 1, let's reduce the equation. That is, let's kill off the denominators, and we accomplish that by multiplying by both sides by the least common denominator. In other words, we need to multiply by a quantity that divides out both, actually x plus 1 to the highest power. In this case we need a factor powerful enough to cancel up to the power 2 in this case. Alright, that should be x plus 1 quantity squared. Right? And so, actually when we distribute this, when we distribute over the first term, see how the x plus 1 squareds cancel out, leaving us with 4x plus 7. And when we distribute over the first term on the right hand side, so essentially this has an invisible power of 1. And well, squared over 1, cancel 1 power, leaving us with 1 power in the numerator, multiplying the a. And when we distribute for the second term on the right hand side, see how both cancel, leaving us with a b. And again, this equation has a special name. It's our basic equation. And this basic equation is the one to be used to find those constants a and b. It's actually a simpler equation than that we have in the previous step. Alright? And here is where we're going to use our number sense. And our number sense right here, well, can we think of a clever number to zero out one of the terms and allow us to find one of the constants? If so, what's that value? How about -1? Sounds good. Because for x equals -1, so plug it in here is going to get zeroed out and allowing us to find the value of b. So let's go ahead and do that. That is 4 times -1 plus 7 equals a times -1 plus 1 plus b. That is -1, -1. That goes to 0. And on the left hand side of this equation, 4 times -1 is -4 plus 7, that's 3, and equals to b. Alright, so that's one of the constants. It remains to find letter A. However, we have an issue here because the issue here is that b doesn't have an x plus or minus some number, right, that we can, cleverly use its opposite in sign to zero out the term and be able to find a. So how do we go about that? Yep. So in this case, we are going to use number 1, the information that we have, which in this case is b, the value for b. Okay. So for b equals to 3, and in this case we can plug in any value of x, your favorite value of x. So what's your favorite value of x in this case? 0. Keep it simple. Of course, you can plug in another number like 5, 29, 17,017,017, your favorite number. It doesn't matter because you will be plugging in on every instance of x on both sides of the equations. And recall that the principle of equations is like the scale, to keep it balanced. If you add 17 grams on one side, you have to add those 17 grams on the other side to keep it in balance. So it doesn't matter if you add nothing, if you add 5, 29, 700 million. But I mean, keep it simple. Don't plug in 17 million to x. Okay, if you want, that's fine. I don't have any issues with that. But 0 is great. So 4 times 0 plus 7 equals a times 0 plus 1 plus b. Oh, but b is known, right? So 0, 0, and 3. So 4 times 0, which is 0 plus 7, that equals to 7, equals to a times 0 plus 1, that's just a, plus 3, and a equals to 4. And score. Alright, we're done with finding the constants a and b that split these partial fractions together. So we may go back to our original problem, the integral of a, which is 4, over x plus 1, and plus b, which is 3 over x plus 1 squared, with respect x. So in this case, let's split this into two integrals together. So 4 times the integral dx over x plus 1 plus 3 integral of dx over, well, you know what I'm going to do? Because, well, do you see how this integral dx over x plus 1 is going to be? Isn't that just some natural log?
Yep.
For the second integral, I'm going to send this x plus 1 to the second power to the numerator as x plus 1 to the negative 2. And in this case, we're going to do a baby u substitution. U equals x plus 1, du equals dx. Well, there's nothing to fix over here in terms of the u du. It's going to work really nicely. So that'll be 4 times ln of x plus 1 plus 3 times the integral of u to the negative 2 du. That's still equal to 4 ln x plus 1 plus 3 integral of u to the negative 2. Well, add 1 to the exponent, and whatever we get, divide that in the denominator. So that's u to the negative 1 over negative 1 plus c. And I'm going to do a couple of things here. Number 1, I'm going to fix the negative exponent and multiply the signs, and also back substitute for u. That's going to be 4 ln x plus 1 plus 3, or actually minus 3 over x plus 1 plus c. So, well, the more we move on through this type of examples, I mean, well, the work, it's not going to be that simple as we did in the previous example. So for the examples we did last time, in which we had distinct, linear, and non-repeated factors, well, it was really easy to just look at the basic equation, find the clever numbers that zero out one of the terms to figure out the other, and you know, that worked really nicely. Over here, especially for the second part of figuring out the constant, well, we needed to think a little bit differently. And it's going to be the same for the next example. All right, so what about the next one? Well, we have the integral of 2x plus 3 divided by this madness x cubed minus 2x squared plus 3x minus 6. Number 1, do we need polynomial long division? In other words, do we have an improper fraction? No. All right, so we're good. Next step, factor the denominator. All right. What do we do when we have a polynomial containing 4 terms? Any ideas here? I think you heard something? Yes. Split it up into like terms. Well, it's already split, and actually we don't have any like terms here because they all have different powers.
Oh, yeah. When you simplify the 3x.
So when we have trinomials, well, we either do the double bubble method or the diamond method depending on the leading coefficient. And when we had 2 terms, well, maybe we had to look whether we have a difference of squares or a sum of difference of perfect cubes. Well, in this case, for 4 terms, let me give you a hint. Factor by grouping. All right? Factor by grouping, what are we going to do here? Factor the GCF of every single group. Factor the GCF of every single group, and then we will have another global greatest common denominator. Well, factor. Number 1, what's the GCF in the first group?
X squared.
X squared. That's going to leave us with x minus 2. Plus, what's the GCF on the second group? 3. That leaves us with x minus 2. Oh, did you see the new GCF?
Yeah.
So that's going to be factored out again, leaving us with the integral of 2x plus 3 over x minus 3 times x squared plus 3. That's what I meant, yes, but not what I wrote. Thank you. All right, so let's have a look at these different factors. X minus 2. What kind of factor is that? Linear. All right. X squared plus 3. Quadratic. However, before we look at this more in depth, Let me give you another example. Let me go with a side trip again. What about x squared minus 25? That's also quadratic, isn't it?
No.
Well, yes, it is, and no. Yes and no, because this can be factored, right? It's a difference of squares. X plus 5, x minus 5, and ultimately that's a sum of linear and distinct, right? Can we do that for x squared plus 3?
No.
For two reasons. There's two reasons we cannot do that x squared plus 3. Number one, x squared plus 3. Well, we can think of this, you know, x plus I root of 3 times x minus I root of 3. We have a couple of issues here. Number one, this factoring that we do to get these constants a and b and c, well, as many as we have, we are looking at factoring polynomials over rational numbers. And the square root of 3 is not a rational number. That's the first issue. The second and most imminent issue here is the I. These are imaginary numbers. And this is calculus of real functions. Don't get me wrong. You will get to see this kind of factorings later in your upper division courses, in your electrical engineering courses, in your physical chemistry courses, when you get to quantum mechanics chapters and all that, when you define all these wave functions. And, well, I don't want to spoil the whole story. But you will work with factorings over imaginary numbers. However, we're not going to do this in this class. So for this reason, we're going to call this, well, number one, linear, and quadratic, irreducible. The other one that we did, x squared minus 25, it was a quadratic, yes, but it was a quadratic reducible to a product up to linear, so that's why it was a quadratic, and at the same time it wasn't really a quadratic because it's reducible, right? Now, so how do we write the partial fraction decomposition for this one? So a over x minus 2 plus bx plus c over x squared plus 3. Well, what is that bx plus c? Okay, number one. So, what's the degree of x minus 2 over here? What's the degree of a? Not 1. 0. So, yes, this a is being multiplied by x technically, but it's an invisible x. This x is there in spirit. Alright, let's summon his spirit, so that's basically x to the 0. Alright? So what do we have? Degree 1, and in the numerator 1 degree less, which is 0. Agree?
Yeah.
Quadratic, 1 degree less would be linear, or 1. Alright? So ultimately what we are integrating here is proper fractions. You know, fractions that, well, in the world of polynomials are defined as the numerator being having the degree less than that in the denominator. Alright? Now, let me make up something crazy here. What about the integral of, I don't know, 7x cubed plus 4x minus 3 over, let me think of something interesting. Yes. That's going to be 7x to the 5th plus 5x minus 1. And let me think of 7x. Let me make it to the 6th. Let's make it more interesting. 7x to the 4th plus, I'm changing these numbers. 4x to the 4th minus 3x squared plus x minus 1. Okay. In the previous example, we got a quadratic irreducible. The quadratic irreducible corresponds one polynomial that is 1 degree less. which is the linear. What do we have here? We have a 6th polynomial, that is a polynomial of degree 6. If we were to write down the partial fraction decomposition of this, it would correspond a polynomial of 1 degree less. What's 1 degree less than 6? So 5th degree, degree 6, a x to the 5th plus b x to the 4th plus c x to the 3rd plus d x squared plus e x plus f. Alright, 7x to the 6th plus 5x minus 1. That's the first setup for the partial fraction decomposition. Now, what about the second factor? We're assuming that these two are irreducible, right? So we can get some of the roots over the irrational, but in this case we're going to get something we cannot do over the irrational. So that's plus degree 4. It would correspond a polynomial of degree 3. That is, okay, what's the next f? Gx cubed hx squared ix plus j over x 4x to the 4th minus 3x minus 1. All right, that's the trend, the pattern. If we were to look at something this crazy, lucky for us, this class only limits to do quadratic irreducible. Cubics, quartics, quintics, we're not going to do anything. The reason I show you this madness here is just so you can see, so you can have a better plot here. So what is this about, So in the worst case scenario. But again, we're not going to do anything this crazy. This is just to pretty much give you a better picture of it. All right, so that's why for a squared, for an irreducible quadratic, it corresponds 1 degree less. All right. Now let's find those constants a, b, and c, and we do that by setting the expression, the integrand rather, on the last step equal to the one in the previous step right here. That is 2x over x minus 2 x squared plus 3 equals to bx plus, oh wait a minute, a over x minus 2 plus bx plus c over x squared plus 3. And again, which one?
On the green one, on top. So that
bx plus c? Oh, 2x plus 3. Yes, thank you. Oh yeah, that's gonna make a whole difference here. Alright, so we need to simplify this equation, and again we multiply both sides by the least common denominator. That is product of quantities powerful enough to divide out both x minus 2 and x squared plus 3. X minus 2, x squared plus 3 will do it. Alright, so let's distribute, and see what's going to happen. Number one, on the left hand side, notice how everything divides out except the 2x plus 3, which will survive over here. When we do the distribution over the first term, the x minus 2's cancel, leaving us with the product of a between a and x squared plus 3. And last but not least, when we do the last distribution, see how the x squared plus 3's cancel, leaving us with, be careful, bx plus c times x minus 2. And this is again our basic equation. All right. And here is where we're going to use every possible clever number, the drill, all right? Try to find and zero out one of the terms so we can find the constants a and b and c. Actually, in this case we have three unknowns. Okay. Can anyone think of a number here? 2. Well, why 2? Number 1, because for x equals to 2, it's going to zero out this whole term right here and will allow us to find the constant a. So that's great because only one number will wipe out two of the numbers, allowing us to do some good work here. Okay, so that's going to be 2 times 2 plus 3 equals a times 2 squared plus 3 plus b times 2 plus c and 2 minus 2. Let me write those 2's with a different color here. So that's a 2, 2, 2, and 2. But this whole term is going to go 0. Okay. 2 times 2 equals 4 plus 3, that equals 7. And 2 squared, which equals 4 plus 3, that's also 7, that means 7a. Everything else got zeroed out, that means a equals to 1. Alright? So far so good? Yeah. So this one worked really, really nicely. However, this is where... okay, so now that we found A, we need to find a way to find B and to find C. Yes?
So I'm a little bit confused. We're plugging in like what seems to be like a random number. Is A always going to equal 1?
Not always. In some, yes, most of the cases that we have done so far have turned out being 1. I think it was the case, or here it was a 4.
For this equation, is A always going to equal 1 no matter what we plug in and stuff?
Well, it depends on the basic equation and depends on the need for the clever values that we plug in. But in many cases we get A equals 1. Yeah, but it's not always 1.
I think I mean more like for these problems. It doesn't matter what we plug in, our x values and stuff, the coefficients are always going to come out. Like, if for example, there's a way to get A with 2 different numbers,
yes,
then is A still going to equal the same for both?
The same, exactly. It's always the same value. Yeah, in this case, well, yeah, for this particular, it's going to be 1. Now, the tricky part right here, and let me make some space over here. So the tricky part right here is to try and find the value of B or the value of C. Well, so number 1, so this one I will just give it away because this one is not that straightforward. So number 1, we're going to use the information that we have for now. Number 1, for A equals to 1, all right, that's one of the pieces of information that we have. And well, let's put a checklist. Let's put check marks rather. So we already have A. We can find either B or C. I'm going to go with C because in this case we are going to choose our favorite value of x. The one that you want, doesn't matter, but preferably one that zeroes out this term bx so we can find the value of C because we already know the value of A, and that will reduce to an equation of one single variable. Can you think of that value? 0. Alright, and x equals to 0, so this is what we do. Number 1, 2 times 0 plus 3 equals A, which is 1, times 0 squared plus 3 plus B times 0 plus C times 0 minus 2. Or not 0, yes, it's 0 minus 2. Alright, so let's plug in those values where they correspond. 0 for x, 0 for x, 0 for x, 0 for x, and 1 for A. Alright? 1 for A. Now, let's simplify this equation. So 2 times 0, which is 0, plus 3, isn't that a 3? And 0 squared, that's 0 plus 3 times 1, that's a 3. And well, our goal is to get rid of B so we can find the value of C. And well, in this case, that's c times 0 minus 2, which is negative 2. And that's 3 equals to 3 minus 2c. And subtract 3 on both sides. We get 0, or actually negative 2c equals to 0. That means c equals to 0. All right? So we got 2 pieces of information already. We are missing 1. So now we need we need to figure out b. Okay, let's put a check on what we have already. So number 1, we figured out a. We already got that one from the first step. On the second step, we were able to find the value of c. So we can use those pieces of information, and well, we can find the value of b. And in this case, by plugging in your favorite value of x, preferably not one that zeroes out this term. Like in the previous step, we used x equals to 0, zero that term, and get the value for c. In this case, well, can you think of another number? Keep it simple. You can plug in 1, 17, 5 million, but come on, keep it simple. So, for a equals 1, b, or rather c, equals to 0, and x equals to 1, this will be number 1. So for x, 2 times 1, 2 times 1 plus 3 equals to a, which is 1, and 1 squared plus 3, plus b, which we want to know what that is, times x, which will be 1, plus c, which we know, and x minus 2, which is 0, 1 for x. So let's write them down. So 2 times 1, 1, 1, and 1. And for a, which equals also 1, c equals to 0. All right? Let's see. So let's simplify this equation and solve it for b. 2 times 1, which is 2, plus 3, that's a 5, equals to 1 squared, which is 1, plus 3, isn't that a 4? And 4 times the 1 outside, it's still 4. Plus b times 1, that's just b, plus 0, that's just b, times 1 minus 2, isn't that a negative 1? Which is, okay, 5 equals to 4 minus b, and subtract 4 on both sides to get negative b equals to 1. That means b equals to negative 1. Alright? So, the moral here, guys, so the more elaborate these problems get, in this case by elaborate, I mean like having different kinds of factors. These are going to get a little more involved, especially when it comes to the part of finding the constants a, b, and c. The last part of the problem, which is the integration, it's all the use substitutions, maybe some trigonometric integration and the like, but I guess the trickiest part is getting those constants. Question?
So I have another method. This part, I was thinking if we can expand all those things into some terms of x squared, some terms of x to the real.
Yes.
And then we compare the coefficient.
Yes.
The coefficient to the left to set up a formula group.
That's true. So in fact, that was my approach when I taught this class the previous 2 semesters here. In many cases, it's shorter to do this finding the clever values to zero out terms. However, in some cases, the clever values it's simply not going to work because the equation is going to get so complicated that simply there will be no way. And in that case, we will have to go through the method that you're talking about. It's called the undetermined coefficient. In fact, the last exercise that I have planned for this section, we're going to use that method. And it's good that you know both methods, especially this undetermined coefficient, because you're going to use it in differential equations when you take that class. You'll see, and you'll see how this works. In the meantime, so what we got? So let me write that integral that we got in terms of a and b. So that's the integral of a over x minus 2 plus bx plus c over x squared plus 3 with respect x. So a, we got what we got for a, isn't that a 1? 1 over x minus 2 plus b, which is negative 1, that's negative x plus 0, x squared plus 3 with respect x. It would be better if we wrote two separate integrals so we can look at the required method for each. That is the integral of dx over x minus 2 plus, or rather, how about minus, because of plus negative, that's going to be a minus, the integral of x over x squared plus 3 with respect to x. Alright, whoops. Let me do x dx instead. Okay, the first integral, it's a very straightforward ln rule problem. The second one, it's going to be a u substitution. U equals x squared plus 3, du equals 2x dx, x dx, 1/2 du. This is ln of x, absolute value of x minus 2, minus the integral of 1/2 du over u. If we take this 1/2 out of the integral, we would be integrating du over u. Isn't that another ln? Yeah. So ln absolute value of x minus 2 minus 1/2 ln of absolute value of u for now. But check this out. When we back substitute for this u, notice that in this case I don't need these absolute value bars. Do you see why? Because this quantity x squared plus 3 it's always going to be positive, so no need for these absolute values to the rescue as opposed for x minus 2. The x minus 2 has the possibility of outputting positive, both positive and negative, but not this x squared plus 3. Question?
If we did something like that on the test, would we mark points off?
For like having?
Putting, like, if we put the x squared plus 3 in absolute value?
No, it's fine. It's still fine, but it's kind of redundant to have. The one that would be wrong anyway would be this one. This one would be wrong because in this case we are accepting only negatives, all right? And I mean positives and not 0 and negatives. And well, this is final answer. All right. So let's see what's next. No.